Today, we're going to unpack a powerful framework that's designed to look past blame and find the real reasons why mistakes happen. It's a total game changer, really, because it shifts the question from who messed up to something much more useful. Why did the system allow this to happen?
When an accident happens, doesn't matter if it's in a cockpit or an operating room, the first thing you almost always hear is human error. But think about it. Is that really an explanation, or is it just a convenient label we slap on something when we stop looking for the actual cause? And that right there is the whole point. Blaming a person? It's a dead end. Sure, it tells you where the system failed, but it tells you nothing about why. And if you don't know why, well, you've got no chance of stopping it from happening again. Real safety means digging deeper. So, if blaming the operator is a dead end, what's the alternative? Well, this is a problem aviation safety pioneers were wrestling with for a long time. They realized they had to stop focusing on the individual and start looking at the entire system that person was working in. So they came up with a model. Let's build this thing together, piece by piece. The first block is S for software. And I don't just mean computer code. Think of it as the rules of the game, the procedures, the checklists, even the symbols on a screen.
Okay, next up is H for hardware. This is the physical stuff, the things you can actually touch. It's the flight controls, the tools, the machine itself. Then we add E for environment. This is the whole context. It's everything from the literal weather outside to the organizational climate inside. You know, the pressures, the culture. And finally, right at the heart of it all, is L for Liveware. And that's us, the people, the most important, most adaptable, and let's face it, the most vulnerable part of the whole system. You put them all together, and what do you get? You get the SHL model. Now, this isn't some newfangled idea. It was actually developed way back in 1972 by Professor Elwyn Egberts. A few years later, a pilot, Captain Frank Hawkins, tweaked it to really zero in on how these different parts connect with each other. It's been a cornerstone of safety science ever since. So we've got our 4 building blocks: software, hardware, environment, and liveware. Now let's really unpack what each of these means, and we'll start right in the middle with the human. So, liveware. Everything in this model spins around this central element, the person. It forces us to ask real questions. Is this person tired? Are they under a lot of stress? Do they have the right training? It's about acknowledging that people aren't perfect, predictable robots. Then you've got the hardware. This is the actual machine. And the key question here is, how well is it designed for a human to use? You know, think about a confusing car dashboard that makes you take your eyes off the road just to change the radio station. That's a potential hardware problem right there. Next up is software. And again, we're talking about more than just code. This is about the rules we're supposed to follow. It could be a ridiculously complicated emergency checklist, or those famously confusing assembly instructions for furniture that always leave you with a few extra screws. That's a software issue.
And finally, there's the environment. This is the big picture. It's not just the physical stuff, like a storm. It's also the invisible forces, like the company culture. Is there a constant pressure to rush jobs to save money? Does management talk a big game about safety but not actually back it up? That stuff has a huge impact.
But here's where the shell model gets really interesting and really powerful. The danger usually isn't inside any one of these blocks. It's in the gaps between them. Errors happen at the edges, where these different pieces grind against each other because they just don't fit together right. Look, when a system is safe, it's because all the components fit together smoothly. The person fits the machine, the procedures make sense for the situation. Human error is almost always a symptom of a mismatch, a jagged edge, somewhere in that system. And this table shows you exactly how deadly those mismatches can be. A liveware to hardware mismatch, that could be a poorly designed control that's easy to misread, leading to a loss of control. A liveware to software mismatch, a confusing emergency checklist that costs a flight group precious seconds when they need it most. And a liveware to liveware mismatch, that's about people. Ambiguous communication between a pilot and an air traffic controller was a huge factor in the Tenerife disaster, the deadliest accident in aviation history. These aren't theoretical, they have real tragic consequences. So what's the big takeaway here? The shell model isn't just a tool for investigating accidents after they happen. It's a whole new philosophy for preventing them in the first place. Instead of just telling people to be more careful, we can use this simple 3-step approach. First, you look at the whole system, all 4 parts. Second, you hunt for the mismatch, the place where things don't line up.
And third, and this is the most important part, you fix the fit. You redesign the tool, you rewrite the checklist, you clarify the communication. You adapt the system to the human, not the other way around.
And this way of thinking doesn't just apply to aviation. It applies everywhere. In medicine, software development, even in our own day-to-day lives. So the next time something goes wrong, try not to just ask who made the mistake. Ask a better question. Why was the system designed in a way that made that mistake almost inevitable? Where was the mismatch?